Okay, let's take a look at our syllabus. Right now, we finished chapter 24, and now we're going to start chapters 25 and 26. They kind of similar, and they are, I think that they're very fun. Mirrors and lenses. And so far, our third exam is going to be 2.5 weeks from now. We had all the way down to chapter, we had the exam to 20 and 21, right? So far we covered chapters 22, 23, and 24. So let's see how far we can go before the third exam. Okay? Notes. Okay, week 13. Lucky one. Can you see this screen here, Vanessa?
Yes.
Oh, okay, good. Okay, so chapter 25, reflection and mirrors. What did we cover in chapter 24? Let's go back here, what we covered here. Oh, right in here. 24, 1, 2, 3, and 4. Okay, that's what we covered so far. Chapter 24. Let's put everything together. All right, so you can have one thing in a single place. Sections for chapter 24. We need now chapter 23. '23. There is a section from chapter 20, right? Let's look for 22 now. And we're gonna paste so far. So far, we have the following material for exam 3. So far, we have the following material for exam 3. 20. Okay, right here. Chapters 22, 23, and 24. And we're getting into reflection and mirror. Let's take a look at the book. Launch. Magnetic wave is going to be 25 here. Okay. wavefront reflection of light, formation of image by a plane mirror, spherical mirrors. Okay, and all those sections here, wavefront. We start with this one, right? Students actually is coming. Okay, so let us behavior of light. Behavior of light. Okay, that's what we want. How do we even better? How do we model the propagation of light? That's what this chapter is all about. Okay, when we are talking about reflection of mirrors, we are talking about what we call geometrical optics. Okay, that's the simplest type of optics that you're going to see in your life. The simple and very intuitive too. It's not that difficult to picture this theory. Okay, the simplest theory of light propagation that you see, that you will see in your life. Okay, and how do we model the propagation of light? We start, we start with a point source. Okay, we start with a point source. And I have here, suppose that you have a point source, a point of light, very small. It can be one of those LED sources that they have a very small area in which the LED emits light. Okay, we say that this point source emits light in every possible direction. Okay, you can picture something like that. And if this source is a distributed light source, has a physical size, right? So we can say that each point of this source, in each point along the surface of the source, behave like a point source that is emitting light in a straight fashion. We represent in geometrical optics, we represent the propagation of light as a light ray. And that's what you're seeing here. Okay. And we can use this type of behavior to predict how images are formed, how images by mirrors and lenses are formed. All right, going back here, we start with a point source. Okay, in geometrical optics, we postulate that light propagates in straight lines, This is represented by a straight arrow. Okay. We start with a planar mirror. Let's start with the planar mirror. So here you go. We have a planar mirror. That's how we illustrate a planar mirror. The reflecting surface is this one here on the left side. The hatched place here means that there is no reflection in this right side of the mirror. Okay. And let's say we have a point source nearby this reflecting mirror. Okay. So let's say we have this light ray that's coming out of the light source and is incident of the mirror at that point in there that you see. Let's call it point I. This one here is going to be point I. And here you go. Let's put it this way. And what else do we do? Whenever it comes to reflection, okay, we must also, not just the light ray, we must draw not just the light ray, but we also must draw a direction that's normal to the surface of the mirror. Okay, and here is the direction normal to the surface of the mirror. I am going to even put the symbol of normal right here. That's the one. A little square. I'm going to put a dot in there. The dot with the square represents an angle of 90 degrees. Oh, we'll use this dot here. Okay. And in the next drawing, what do? I introduce you to one of the laws in geometrical optics. But before, let's call this angle here the incident angle, theta incident. The angle is measured with respect to the normal, okay? Bring this thing a little bit lower. Yeah. Good. Oh. Okay, and then what else should you know? Well, you should know a very important law of geometrical optics. That is the angle of incidence is equal to the angle of reflection. Okay. We started with this important result in geometrical optics. Start the planar mirror, right? First, we draw a mirror. Okay. With one of its sides hatcheted. Okay. The hatchet surface does not reflect light. Okay. We draw the source, a given distance from the mirror. Distance from the mirror on the side facing the unhatched surface, right? A light ray in any direction. A light ray propagating towards the mirror. Okay. 3, 4. The direction normal to the surface of the mirror. Okay. The incoming ray, light ray propagating towards the mirror. This income, let's put here. This incoming ray is called the incident ray. Direction normal to the mirror. The angle between the incident ray and the normal is called the angle of incidence. That would be theta incidence. Like that, theta incidence. And now very important, because light is being reflected out from the mirror, comma, we must also have a reflected ray, right? For mirrors, the angle of reflection is equal to the angle of incidence. Some people call that the law. I'm going to put between quotes because it's not exactly a law. The law of reflection. It's possible to derive that. That's why I put it law between quotes. Okay. So we can go back to our drawing. Here you go. The angle of reflection is equal to the angle of incidence. Can you remember that? Not difficult, right? And that's just one light ray. Okay. So what are we doing here? You know, we start with a planar mirror. And what are you doing here? I'm going to tell you right now. Let us locate the image of a point source. That's what we're doing here. Okay. Let's locate the image of a point source. The image, the position, right? The position of an image, of the image of a point source. First we draw, you know, and we go through this process. Draw a mirror, the source at a given distance from the mirror, a light ray, the incident ray, direction normal to the surface of the mirror, the angle between the incident ray and the normal, and the reflected ray. And let's not forget, the angle of reflection is equal to the angle of incident. And I'm going to spell that right in here with an equation. Theta of reflection. I'm going to put REFL. Okay. There's a reason why I do that. Is equal to the angle of incidence. What's next? And then, let's see, first we draw. Okay, I'm gonna start with our first light ray. We need more than one light ray. Okay, here you go. And now I can put that. Now we draw a second light ray coming from the source. Let's go back here. Any light ray in any direction. Okay, so here you go. Here's the second light ray. I'm gonna go step by step. Here you go. Second light ray is this one here. And the second light ray is undergoing reflection as well. Just like the other one. And just like before, the angle of incidence is going to be equal to the angle of reflection. That's what you're going to see right in here. Okay, this angle of reflection is equal to this angle of incidence. We can also draw a third ray, but you don't need to. Okay. Now draw a second light ray, repeating the steps 3A through 3E. Okay. You can also draw a third light ray just for practicing purposes. Just for practicing purpose. But it's not required. It's not required. Okay, and that's what I did in my notes here. It's not required to solve the problem. The third light ray, the blue light ray that you see right in here. So here you go. And in all cases here, in all those three cases, the angle of incidence is equal to the angle of reflection, okay? Now, to find the position of the image with respect to the source and the surface of the mirror, we do the following. 1A. Let's see. We extend at least two of the reflected light rays. That's what we do. See, we're extending into the region behind the surface that's being reflected. I did that for this light ray. I did that for this light ray. I did that for this light ray. And if I do everything right, okay, I'm going to find a point. The point of intersection of those light rays is going to be the position of the image that I'm labeling as S prime. Okay, that's a very nice technique that applies not just for planar mirrors, but also applies to curved mirrors, either convex or concave. Okay, we usually, let's say, we usually dash those lines so it's not, so it doesn't let me move a little bit. We usually, those light rays that are behind the reflecting surface, we usually dash them, okay? Just like this one as well. I'm going to, here you go. It's a little bit, the source is a little bit higher, right, than what I had drawn. So practice this technique many times. And we have this one as well. Dash. Like that. I'm going to shorten this light ray. Like that. That's the position. Well, it happens that the position of the image is at the same distance as the position of the object, okay? For the planar mirror. For the planar mirror. And here you go, we have what we call, and we can repeat that, just not for a point source, but we can also repeat that for extended light source. And that's what you're going to do that. Okay, we draw the mirror again. But before we go into that, let me document that in my notes, right? Here you go. Now to find the position of the image with respect to the source and the surface of mirror, we do the following. A, extend at least two of the light rays behind the mirror, okay? The intersection of these two light rays corresponds to the position of the image of the object, right? Or object or point, in our case, point source of the object. Okay. We're doing for a point source. Okay. To locate the position of an extended source, to locate the position of the image of an extended source, the procedure is similar. And I'm going to repeat that with you. Here you go. Here is a representation of this extended source. I label it as O as the object. Okay. Let's take a look at the book, right? Here you go. How they do that, what the reflection of light rays. Here you go. Angle of incidence is equal to the angle of reflection, right here. Okay. That's a surface that's planar, and this is a surface that has a bunch of bumps. You can see that because we have different angles of incidence for each of those light rays. You know, the light rays are not going to end up being parallel. Okay, light rays of same angular incidence they're not going to be parallel. Okay, formation of an image by a planar mirror. Here you go. Here you go. Here's my extended object. Okay, and here's the image of the extended object. This image behind the mirror is called the virtual image. So let's write that down. Images located behind a mirror are called virtual images. Okay. And then there is another type of there is virtual image and real image. You know, in opposition versus real image, which we'll discuss later on, which we will discuss later on. Okay, so let's look at the position of an image of an extended object. Here you go. The extended object is represented by an arrow like that. We label it as being the O, or the object, O for object. Let's see how the book has. He didn't give you a. Let's see if he did that for. No, he's just using drawings. He's not using arrows, right? But here would be the object. Here would be the image. This would be the object. This would be the image, and so on. Okay, object and the image. Oh yeah, he has here object. So we go ahead. What we do? We draw a planar surface. In this case, we draw an axis of the mirror as well. One more step here for this one. Draw the object in front of the mirror. And what am I doing here? I am documenting the position of the object, d sub a, sub o, which is the distance, right? And here what I'm doing, I am showing a light ray that comes out from the tip of the object, upper tip of the object. Okay, angle of incidence in this case is going to be 0 degrees. So the light ray reflects on itself. Okay, reflects on itself. And then we go ahead, we need at least 2 light rays to find out the position of the image. Now we have this other light ray that's incident at the center of this mirror and is going to be reflected in this direction. Okay. If we want to find out the position of the tip of this object, what do we have to do? We have to extend to the right side the light ray and the intersection of those 2 light rays is going to be the position of the image. Object, O for object, I for image. That's called the axis of the mirror, this one here. Okay, and this distance here of the image is going to be d sub I. For a planar image, for a planar mirror, the distance of the image is going to be equal to the distance of the object. Okay? So, to locate the position of the image of an extended source, the procedure is similar. Okay, for a planar image, for a planar, not planar image, planar mirror, the position of the image is equal to the position of the object. To the position of the object. And now we can start talking. Now let's talk about what we did so far. Start as a planar mirror, the simplest of all mirrors out there. The simplest of all mirrors out there. Next, we cover a concave mirror. Concave mirror. A concave mirror, a spherical concave mirror. Okay, spherical, very, very important here. So let's go here. How a spherical concave mirror can be represented. A spherical concave mirror can be represented, can be visualized by thinking of a sphere of radius r. This radius r is called the radius of curvature of the mirror. Okay, we section a piece of the surface. Think about that. I want you to visualize how a concave mirror is formed, a spherical concave mirror. And what we have is just like a hubcap from a car, right? We go ahead and make the surface aluminized so it can reflect light. And we hatch the other side of the surface. So we have a section of the spherical surface. This mirror that's formed here is going to be a concave mirror of radius of curvature I. Okay. So consider a sphere of radius of curvature R. If you section, if you cut, right? If you cut a part, a hubcap, okay, let's put here, a hubcap of this sphere, comma, you have a spherical mirror. you have a spherical mirror. If you cut the hubcap of this sphere, we gotta do something else, and make the inner surface of this hubcap reflecting, you have a spherical mirror. You can buy spherical mirrors at your drugstore. You can buy a spherical mirror. It's the same mirror. It is the same mirror that amplifies your image. Okay? Let's take a look here. In the internet, spherical mirrors for sale, right? Let's take a look here. Okay, here you go. The spherical reflector mirror, the hubcap that I mentioned to you, right? The inner surface is reflecting, is made reflecting. This, this surface is spherical, $30. If you look at this towards this surface, your image is going to become amplified, larger. That's another mirror here that's used for telescopes. See, astronomical telescope. Okay. And those are high quality mirrors. They're kind of, expensive, more expensive than the regular ones that we find out there in the drugstore. Okay. Now, the question is, how do we predict the position of an image produced by a spherical concave mirror? Okay, that's the question. Well, the answer is very simple. We use exactly the same techniques discussed above for the planar mirror. Although it's a little bit, although it has some other details that do not show up for the planar mirror. Okay, so I'm going to walk you through that. Okay, so here you go. Notice that this arrow, right, is going to be perpendicular to the line that's tangent to the surface of the mirror. Okay, because it passes through the center of the mirror. Okay, so if you have a light ray passing through the center of curvature of the mirror, it's going to reflect on itself. Can you picture that? Right? Here you go. Same thing here, right? Exactly what I said. Light ray passing through the center of the mirror is going to reflect by itself, on itself. Angle of incidence is going to be 0 degrees. Angle of reflection is going to be 0 degrees as well. Tangent to the spherical surface. Plane tangent to the spherical surface. And here you go. That's how we usually represent a concave mirror. We represent the concave mirror as a planar surface with those lines here. Okay, we hatchet the behind the mirror. We hatchet to just to state that there is no reflection on the side. We put an axis for the mirror as well. We draw an axis of the mirror that passes through the center of the mirror. We draw the center of curvature of the mirror. is important. And then we start playing with different types of light rays, okay? Start playing with different types of light rays. We start with a collimated light ray. Here you go, a collimated light ray is going to be reflected towards a point that's midway between the center of curvature and the mirror. Okay? Fine, so we're doing here. Finding the position, and not just the position, but also the size of an image produced by a spherical concave mirror. Okay? The first thing you have to know, is how different light rays behave with respect to the mirror. Okay? So I already told you that light rays that pass through the center of curvature of the mirror reflect on itself, because what? Because the angle of incidence is 0 degrees with respect to the normal direction. Good. Light not just reflect on itself, but reflects towards the center of curvature. Okay? Light rays parallel to the axis of the mirror, reflect towards a point that is between the center of curvature and the mirror itself. Okay? This point is half the distance of the center of curvature, and is also called the focal point of the mirror, represented by the letter F. Okay, so here you go. Let's see here. Okay. That's C prime. I'm calling this one C prime. Okay. I will call this one here, this point here, F. F of focal point, capital F. So what else? Here you go. I have it here, capital F. All those light rays parallel to the axis of the mirror, they reflect towards the focal point. This light ray reflects toward the focal point, this parallel X-ray reflects toward the focal point, and so on. Okay. And one more thing. Light rays that passes through the focal point reflect parallel to the axis of the mirror. Okay? Right? It's kind of complementary from the other one, right? So here you go. Light rays parallel to the axis of the mirror reflects toward the focal point. If you trace it back, you're going to get exactly the same thing. Okay? If you trace it back, all I have to do here is to change the direction of this light ray. Okay? Format shape. Let's see. Format shape. Right in here. This one. Okay, and format shape too. This one and this one, like that, right? I'm gonna change the direction of this light ray as well. You go, this one and this one. Okay. And this one as well. This one and this one. Here you go. Here you go, radius of curvature R, focal point, and then what you have here is the focal distance. Okay, light rays. This give rise, this point is R divided by 2. Okay, this distance, R divided by 2, is also called the focal distance of the light ray. The focal distance of the light ray. By the same token, that parallel light rays reflect towards the focal point F, light rays that pass through the focal point are reflected parallel to the axis of the mirror. Okay, so we have 3 different light rays. There is one more that we can, light ray that pass through the center of curvature, light ray that parallel to the axis of the mirror, light ray that pass through the focal point, and there is one more light ray. Light rays incident at the center of the mirror are reflected by the same angle. So 4 different light rays that we can play with to find out where the image of the source is formed. Okay, let's see if I have it here. There we go. Oh yeah, this one here. At the very center of the mirror. Okay. It can be this light ray. It can be. What did I do here? Yeah, can be this other light ray. And all you have to do is to reflect that. See, let's see if I can reflect it. Size. Size position. Let's see. There might be a way to reflect it without going through the trouble. Okay, I'm not going to reflect it. Otherwise, it's going to take too long. Here you go. Second light ray. Like that. I'm going to put it different colors. Okay. I'll put this one black. Okay, so now you gotta memorize that, right? But it's not difficult to memorize. It kind of makes sense too. All those 4, all those 4 types of light rays, they are just obeying that law of reflection, okay? They're just obeying that law of reflection. A light ray that passes through the center of curvature of the mirror reflects on itself, because when the light ray reaches the surface of the spherical mirror, the angle of incidence is going to be 0 degrees with respect to the normal. That's why it reflects on itself. Here's the same thing here. Light ray parallel to the axis of the mirror is going to reflect towards the focal point, because that angle of incidence is going to be equal to the angle of reflection. The difference is that the surface of the mirror is curved, right? And the same thing applies to the other ones. Let's take a look at this one here. Here you go, a mirror, axis of the mirror, center of curvature of the mirror, focal point. You're going to need all those points here. And here you go. Here's my object. Just like I did before for the planar mirror, okay? The idea here, find the position of the image of this object using all, at least two of the light rays that we discussed, okay? We usually start with the light rays that are parallel to the axis. Those light rays, we say they are collimated light rays. Don't forget, those light rays, they have to reflect towards the focal point. That's half the distance. Half the distance of the center of curvature. Here you go. First light ray. And then you can choose your second light ray from any of those three that we mentioned, okay? It can be this light ray here, okay? That's gonna reflect parallel. It can be this other light ray that's gonna reflect on itself. Let's see, I didn't put the fourth light ray, right? It can be the fourth light ray that's going to be incident right here at the middle, okay? Here you go. Here I'm marking by the way, going back here, notice that all those light rays, they intersect at a given point. Do you see the point of intersection? I'm gonna point of intersection of the light rays. I'm gonna point that out to you. Here you go. Point of intersection of the light rays. Point of intersection of the three light rays. Intersection of the three light rays. So what do we do with this point of intersection, right? Here is the distance of the object. Here is going to be the distance of the image. Okay, so at the point of intersection, we draw an arrow that's going to be the image of this object. Okay, I should make it. Why it doesn't? Oh, well, I cannot mark that for some reason. I don't like that. Well, you can see that, right? Let me change the color, right? So it becomes more easy to see this object. Didn't change it. Okay. Okay, I know what's happening here. This object here is behind, so I have to bring to the front. It doesn't help, huh? Yeah, it's this line that's getting in the way. Okay, now we can see the object more clearly. There you go. Not the object, the image more clearly. If this one here is the object, this one here is going to be the image. That's how we determine the position, just by using this little trick, this little geometry trick. But if you want to know exactly the position of this image, we use a very simple formula that's easy to memorize. Okay. So here you go. First thing you have to know. So let's document step by step, right? Find the position of the image of a given object in front of a spherical concave mirror, right? What do you do first? Draw the mirror, draw the axis of the mirror, draw the center of curvature of the mirror, draw its focal, okay, the center of curvature of the mirror at a distance r from the mirror, draw its focal point f at a distance r over 2 equal to the focal distance. Draw the object in front of the mirror. Now that we have drawn the object, use at least 2 light rays to locate the position of the image of the object. Okay? Parallel light rays reflect towards the focal point. Light rays that pass through the focal point reflect parallel to the axis of the mirror. Light rays that pass through the center of curvature C reflect on itself, right? On itself. And 4, light rays incident at the center of the mirror reflect by the same angle. Okay, so you have 4 light rays to choose from. Once you choose you have 4 light rays that you can choose from, and you need only 2. Remember that? The intersection of these light rays correspond to the position of the image. Okay, and there is a simple formula for that. A simple formula for the position of the image. This formula can be derived. This formula can be easily derived using geometry arguments. Okay. And what is this formula? Okay, I'm going to use the notation of the book. Okay, here you go. Concept mirror equation. That's the one here that we want. Mirror equation. See, we are going to use this notation here. Focal length of the mirror. The equation is okay. Here you go. For the position di let let f d naught and di, let f d naught and di be the focal distance of the mirror, the position of the object with respect to the mirror, and the position of the image respectively. Object and the position of the image with respect to the mirror respectively. There is a simple formula that relates those two quantities, okay? That relates these three quantities, which can be derived using geometry argument. I'm not going to derive it here. And the equation is like that. Can you remember that? If you memorize, it's easier for you, it's better for you, okay? Inverse of the focal distance is equal to the inverse of the distance of the object plus inverse of the distance of the image. Okay. So there are two ways, right? Either you draw it and then you go ahead. If you do everything right, all you gotta do is to measure this distance here with a ruler, or you use those equations here, right? That's the distance of the object, that's the distance of the image. And I'm gonna go back. Here you go, put it right in here. Okay, and that's for an object that's further from the center of curvature. As we progress here in this material, I'm going to tell you, it's going to become clear what happens when we move this object back and forth, okay? You're going to see it. There's a nice relation for the position of the images when we move this object back and forth. Do you have any questions? What I want to do now, I want to take attendance. Today is the 29th, almost May. Semester is almost over. Let's see. Jacqueline, are you there? Jacqueline, hello, Jacqueline. Okay, good, you're there, right? Thank you. Oh, by the way, I posted the correction. Oh, I didn't say that. I should have told you that. Let me finish here the attendance and then I'll tell you. I don't see Sky, right? Sky is not here. Ashley, are you there? Thank you, Ashley. Corina, are you there? Thank you. Norberto Lopez. I don't see Norberto. Next is Vanessa Mena. She just here. Thank you, Vanessa. Yorgo.
Here.
Thank you. Lisel. I don't see Lisel here. Paul Zapata. Hello, Paul. Just say you are here. Let's see, 6 students. Yeah, so let me tell you something here that I didn't tell. I should have told you at the beginning. Let me go here at the beginning. Okay. Monday. Okay, here you go. Sky is coming. Okay. I corrected reports. The reports for labs 4 and 5. Okay. Hello, Sky. Are you there?
Yes.
Okay, thank you. Sky. Here you go. 7. Okay, so I correct the report for labs 4 and 5. But one important point here. The correction for lab 4 is in the .html format. However, the correction for lab 5 is in PDF format. I finally figured out. It looks like the Excel finally managed to fix the PDF format of Excel. Looks like, because I tried it a long time ago and never worked. So from now on, I will be posting the corrected reports in a PDF file, okay? PDF file format. However, here you go. That's the message I want to pass to you. And but the correction for lab 4 is to HTML format. Okay, I think the PDF format is better, is more convenient than a HTML format, because it's just all you need is a single file. Okay, and we can go for our break. Right now it's 9:57. Any questions? Break from, okay, Paul, I gave you attendance. Let's see, 57, 55 to 10, 12, right? Yeah. 10, 12 a.m. So I'll see you in 15 minutes. I am back here. Okay, did you get the idea? How I'm going to elaborate a little bit more. You know, let me write that down here. There are a bunch of simulations for mirrors, concave and convex for mirrors, both concave and convex, and you can play a little bit with these simulations to get a better feeling of how the above equation behaves, okay? And there is one of those simulations right here. This one here. Okay, problems of this, problems of mirrors. Basically, you know, reduces to finding the position of the image, the magnification, and its magnification. Let's see, its magnification, and whether the image is real or virtual is magnification, whether the image, okay, whether so far the image is inverted or not. Okay. So that are the problems that we are going to find out there, okay? Reduce to finding. One, here you go. The position of the image. One, the position of the image. The magnification of the image. Three, whether the image is inverted or not. And four, whether the image is real or virtual, okay? And I'm going to cover that right now. Let's take a look at this drawing right here. Okay, you can see that the image is in the same side as the object. Okay, so and if for a mirror, here you go, for a mirror, if one, the image is in the same side as the object is, the image is considered real. Okay. Another characteristic of a real image is that it can be projected into a screen. Okay. That's an important characteristic of a real image. So any projectors like the one in your movie, any projectors like the ones in the movie theater, project an image in a screen, and consequently, the image is real. Okay? On the other hand, if the image is on the other side, right? Is on the other side of the mirror. The object is on the left and the image is on the right side of the mirror, okay? If the image is on the other side of the mirror, let us say if the object is on the left side of the mirror and the image is on the right side, we say that the image is virtual. We're going to see virtual images very soon, okay? For the case we illustrated in the PowerPoint, image is real, inverted, is smaller, and between, here you go, let's take a look here at our image. Okay, here you go. The image is real because it's in the same side that the object is located. And we can also, project it into a surface. Inverted is smaller than the object. Okay. And on the top of that is between the center of curvature and the focal point. And its position is between the focal point and the center of curvature. Okay, But there are, like I said, there are other images. Let's take a look at our simulation here, okay? Those simulations are real handy are very good to understand how a mirror behaves. Here you go. Here we have the case of a concave mirror, a spherical concave mirror. Here's the focal point. Here's the center of curvature. Okay, CC stands for center of curvature. Let's see what I can do here. Let's see if I can larger. Yeah. Okay. Focal point, center of curvature. Take a look here. You know, the focal point is at the position -4. The center of curvature is at position -8. Notice that the focal point is half the center of curvature, the distance of the center of curvature, right? And here's my object, okay? Let's see if I can, oh gosh, I cannot move it. Oh, too bad. Oh no, that's the object. The object is this one. Sorry, folks, that's the object here. Okay, I can change the size of the object. I can change the position of the object as well, right? So how many light rays is he using? He's using 1, 2, 3 light rays. Okay. The light ray that pass through the center of curvature reflects on itself. The light rays that pass through the focal point reflects parallel to the axis. The light ray parallel to the axis reflects towards the focal point. Okay. So let's play a little bit here. Here you go. This image. There are, you know, basically there are I'm going to show you how many positions we have here. There are only 1, 2, and 3 positions for a given, 3 distinct positions for a given object, okay, in a mirror. If the object is further away from the center of curvature, the image is, the position of the image is going to be between the center of curvature and the focal point, okay? And on the top of that, the image is also going to be real and inverted. Make sense? Okay. So as we move towards the center of curvature, look what happens to the image of the object. It starts to grow larger and larger, right? Not only grows larger and larger, it also approaches the center of curvature. The position of the image approaches the center of curvature. Right now, this image is 3 units high. This object is 3 units high, and the image is less than 2 units high. Okay. Height of the object is 2.96. It's not exactly 3, but it's 2.96. Height of the image, 1.76. It's a negative sign because it's an inverted image. Okay. As we keep on approaching the object, look, watch what's happening. The image keeps on growing, right? Until it comes to a point where if the image is located exactly at the center of curvature, the object is also going to be located at the center of curvature. Okay? See? Distance of the object, 8 units. Distance of the image, 8 units. Okay? Height of the object, 3 units. Height of the image is -3 units. That's exactly and the magnification is going to be exactly 1. Okay? Here, you know, the magnification of the object is less than 1. Because the image is smaller than that of the object. Okay? So here you go. As we keep on approaching the object, moving the object towards the focal point, the object between the center of curvature and the focal point, now the image becomes magnified. Okay? Look here, the height of the image is 3.5 units, more or less, right? Here is 2.96 units. So there is a magnification of the image. As you get closer and closer, oh, and also don't forget, right? The position of the image is past the center of curvature. The further the image is from the center of curvature, the larger it becomes. Okay, so here you go. Look what happens right here. And now the image, is out of the bounds, right? Out of the bounds. But note, see that the image keep on becoming larger and larger, right? As I approach the focal point. Okay, look at the height of the image, 17 units, almost 18 units. Here, the height of the object is 3 units. Look at the distance, right? By the way, this divided by this is going to be this divided by this, okay? Minus, actually. And now, when we get exactly at the focal point, what happens? The size of image becomes infinitely large. They put a question mark here. But the reality is that, notice that those light rays, they are parallel to each other. Because they are parallel to each other, it means that they are intersecting each other at the infinity distance, right? So ideally, they should have put here infinity here. And here too should be infinity, okay? So far we covered 2 regions, right? 2 regions, and we have those 2 points at the center of curvature and at the focal point. But now that we are at the focal point, if you keep on approaching the object, if you keep on moving the object towards the mirror, the image ceases to become real and start to become virtual. Okay, notice the dashed lines here. The image is forming behind the mirror. Okay, and there is a magnification here. There is a magnification. The position of the image is minus 35. Upright, the image is upright. See that? Is a virtual image. Let's get closer and closer. Okay, and here you go. We start to see the image coming into place here. Okay, and then as we're touching the mirror, the image coincides with the object. The position of the image coincides with the position of the object, and consequently, they're going to be almost the same size. Okay, that equation that I showed to you reflects this whole story here that I'm telling you, right? So let's summarize what we saw here. And by the way, let me tell you, let's see. Let me get the other equations for you. Yeah, we have something like that. Not only we have this equation, but we also have this other equation here that I obtained using geometry, similar triangles, okay? So the height of the object divided by the height of the image is minus the distance of the object divided by the distance of the image. Okay, and we have also this parameter that we call magnification. Magnification M, okay, is given by this equation. Magnification is a positive number, okay? Those are the 3 equations that you should know. So let's apply this equation here for all those different types of positions, right? So find the distance of an image for the following conditions. Consider, here you go, example. Consider a mirror of focal distance f, right? Distance f. Find the distance of an image of the image of an object whenever a and radius I'm gonna put radius of curvature r from the mirror, right? Find the distance of the object from the mirror whenever of the image of an object whenever the object is the position of the object is, oh, here you go, DO greater than R. Should be lowercase d, okay? DO greater than R. Greater than R. Yeah. Okay, gotta do that. Okay, greater than R. Agora, DO greater than R. DO equal by the distance equal than R. You know, R greater than the O greater than F. DO less than F. Okay, 1, 2, 3, 4. We still have one more here. DO equal to F. DO less than F. Okay, and now I gotta put a lowercase here. DO DO F F F DO R R R. Everything that we're going to do here is going to show exactly, what the simulation shows us, right? Solution. Okay. Let's get the equation right in here. Okay, that's the equation that we want to do. We're doing that for item A. Item A. Okay. D naught is greater than R. Let's not forget that F is R divided by 2, right? So I'm going to write it down. R divided by 2. So we get 2 here upstairs, R downstairs. And we want to find out DI. Okay, so here we go. we work the details of this equation right here. And what I do, I'm going to pass the d naught to the other side. Okay? And then we have to invert this equation here to find out what di is going to be, right? I'm inverting here, and in addition to invert, I have also to put this one. Let's see how I'm going to do that. You know, let's keep on. Let's work on the left side first, and then we invert it afterwards. Yeah. Put common factors here, right? D naught. R D naught divided by R is D naught. Consequently, we have 2 times D naught minus R, right? And now we can invert. We can invert and look at how the equation behaves and study how the equation behaves. Di goes to the other side. R D naught goes to the right side. D naught minus R goes to the right side. And that's what we get for Di. Okay? Okay, if D naught is greater than R, okay, this what you see right in here is going to be 2R minus R. So this thing is going to be always positive, right? Always positive. Okay. And so I'm gonna go another, I'm gonna write down like that. 2D naught minus R is going to be, let's say, a C times R, where C here in this case is greater than 1. C greater than 1. Right? Because D naught is greater than R. Here we're going to have 2R minus R. So this C here that you see right here is going to be a number greater than 1. Okay, and now we can cancel out the R with the R. And what are we getting here? We are getting here that Di is going to be D naught divided by a number greater than 1, right? If it's a number greater than 1, it means that Di is going to be less than D naught. Okay? Less than D naught. That's exactly what we saw, right? If the object is past the center of curvature, Di will always be less than D naught. Okay. And then we can find out about the other parameters as well. The other one is going to be this one here, right? You go. H naught over Hi is D naught minus D naught divided by Di. Di is D naught divided by C, right? Go. C is a number greater than 1. And then what we get? We get minus C. What does it mean? It means that the height of the object is greater than the height of the image. Okay, and the negative states that it's inverted. Okay, negative sign means, oh, by the way, di might be less than d naught, but di is also greater than 0. Very important here. This C it should go right here. Should go right here. Okay. Because di is greater than 0. Comma. It means that the image is real. Okay. Means that the image is inverted. Okay, this negative here means that the image is inverted. The magnification, we have the magnification. Here you go, here's the magnification. Wait a minute, the magnification should be all the way around, okay? Let me fix that. Let's see how the book did. I want to do according to the book. Let's see. They don't say anything about magnification here, huh? Image, oh yeah, here you go. Image height divided by object height, okay? So we gotta do that. Is image height, it's all the way around. Image height divided by object height. Same thing here. O. Okay, we gotta fix the other equation over there too, right? Right in here. Okay. If the HI is greater than H naught, then we have a magnification, okay? And what would be the, here in this case, what would be the magnification? Okay, in this specific case, the magnification would be 1 divided by C, right? 1 divided by C, like that. Which is, by the way, is less than 1. That's what happens when the object is past the radius of curvature, okay? That's one region. What about the next region? Not the next region, but the next point, right? Okay, the next point is what? D naught equal to R. All you have to do is substitute that in the equation. We got D naught equal to R. We're going to substitute that in the equation, and you're going to get exactly what you saw in the simulation. Okay, here you go. D naught is going to be R. What's going to be DI? We pass 1 over R to the other side. We have an equality here. 1 time minus the other is going to be 1 over R. And just like you saw in the simulation, the distance of the image is going to be exactly R. The image is going to be located at the point of curvature. Okay, so where is the eagle? Object at the center of curvature, the image at the center of curvature. Okay, and we can even write like that, right? In the next one, here you go. H naught over HI is going to be equal to -1. Okay, exactly equal to -1. Here's image is real. Image is real. Image is inverted. And then we have the magnification. It's going to be exactly equal to 1. That's item B. What about item C, right? Item C is going to be D naught less than R, greater than F. We go ahead and analyze this equation again, right? So here we go. Oops. Less than R, greater than F. Now it's all, let's see. No, it's all the way around, right? Like that. I have to fix that. Yeah, that's right. D naught, yeah, okay, good. So let's say I'm going to write D naught, let's write D naught in terms of a parameter. Let's see, let me choose a letter here. Not E, F, G, yeah, G, GF, okay? Where G oh yeah. G is gonna be what? It's gonna be greater than 1, less than 2, right? And we can even go the next step here. And don't forget, focal distance is going to be R divided by 2, right? Now we go ahead and replace D naught GF, which by the way is going to be GR divided by 2. Okay. And I'm going to put it in the equation above. No, leave it here. Next step, negative equal. And I'm going to combine those two factors here, G and G, right? Same denominator. When you get the same denominator, we can put them minus, okay? Can put them in the numerator. I want this one right in here. Right here. And now we can invert our equation. That's the equation here that you want to look at. Di GR on the other side. I can also put the 2 in evidence here. I didn't do that, but I'm gonna do that right now. And this one becomes 1, right? Don't forget, G is between 1 and 2, right? G is between 1 and 2. Greater than 1, less than 2. And what happens? This term will always be less than 1. Always be less than 1. Okay? And okay, I'm gonna separate the terms here. Okay, here you go. I'm gonna separate this way so we can analyze it better. Okay? This term here will always be less than 1. Greater than 0, less than 1. Consequently, this ratio here is going to be greater than R. Okay? This term here is going to be anywhere between half and 1. Half and 1. Okay? Consequently, that implies, right, that the image falls between this interval here. Okay? And the magnification will always be greater. Okay? And that's item C. Let's see here. Let's get the magnification here. Let's see. Yeah, that's DI. Let's put the DI right here. And the D naught between F and R. And D naught is GF, right? Or GR over 2. GR over 2. I'm gonna put the order. Okay, I want this one here. And we can go ahead, cancel this one and this one, right? When we cancel, we get something like that. Good. So less than 2. So what we are going to do here? Okay, this guy is going to be, okay, what you see right in here is anywhere between 0 and 1. That's what you see here, right? If G is equal to 2, this guy ends up being 1. If G is equal to 1, this guy here ends up being equal to 0. 1 divided by 0 is greater, right? So it's going to be anywhere greater than 1, okay? So it matches exactly what we got there before, okay? And item D, let's go, item D, here you go. Now you got the idea. I'm gonna, you know. So here you go. Image. Let's see. Okay, here implies image real because the I is positive, right? The I is positive. Here, image magnifier, and so on. Okay. Let's the next item would be, you know, those two here. Item D, and this one should be item E. Okay, if is exactly equal to F, what do we get? I'm going to put it 1 divided by F here. If D naught is exactly equal to F, right? We can pass this term to the left side. When 1 minus F cancel out, we get 0, right? And what does it mean? It means that di goes to infinity. We call that improper image. Goes to infinity. Infinity right here. The image is called improper. Okay. And what else? We have, let's see. Let's work the magnification. Called improper. Okay. Just like before, the magnification is going to be almost infinity, right? And finally, the last one. Those are all the cases that you're going to see in this course. Okay, let's get the, let's get this one here. I'm going to put 1 over F. Okay. Now, D naught is going to be less than F. Because D naught is less than F, when we pass the inverse of D naught to the left side, something interesting is going to happen, right? Because D naught is less than F, it means that 1 of D naught is going to be greater than 1 over F. And what does it mean? That implies that this thing must be less than 0. This term less than this term, right? And what does it mean? It means that di is going to be less than 0 as well. Okay, the image is virtual. The image is virtual. And let's but let's finish here. We can write down the I in terms, let's let's see here. Here, I'm gonna write that down as a number. Let's see which number, H, F, okay? Like that, whereas H is less than 1, right? F is, D naught is less than F, so we can express that in terms of this parameter H, that's a number less than 1. Less than 1, greater than 0, right? Less than 1, greater than 0. And we go ahead, get everything here under the same denominator, right? When you get under the same denominator, we get something like that, right? And then we can invert the I goes to the other side. FH goes to the other side. Okay. When H is exactly equal to 1, the image becomes improper. We don't need that anymore. But whenever it's less than 1, we have this ratio here. I'm going to put like that, H. We have this ratio here. It can be anywhere. We have this ratio here, and now we can apply for the magnification. Magnification, let's see, D naught. DI upstairs and D naught is going to be HF, right? HF. HF upstairs cancel out with HF downstairs. And we finally have this one here, which is always greater than 1. Okay? The image is always magnified. That's exactly what we get here, right? As the object. Here you go. As the object is here in this region between the mirror and the focal point, its magnification will always be greater than 1. Okay? It's going to be only equal to 1 whenever the object is exactly at the surface of the mirror. So we look at the 3 regions and 2 points. That's what we did. We looked at 3 regions and 2 points. Okay? We analyzed the equation for 3 regions and 2 points. 1106 right now. Let's see, any questions about that? Okay, that's what we did for concave mirrors. Next one is going to be convex mirrors. Next, let's see if I can finish that. Convex mirrors. You go. And by the way, all this treatment, you can do that in those drawings that I'm going to show you, right? That I'm showing here. Here you go. See, the object passed the center of curvature. The image is formed right in here. Okay. the object at the center of curvature, the image formed exactly at the same point as well. And now we can start looking at convex mirrors. That's the symbol for convex mirror. In the case of the convex mirror, the center of curvature is to the right. Okay? And then we have the reflection of the center of curvature on the other side. We have this focal point, right? F prime, and the other focal point on the right side. And we go ahead, we do exactly the same thing. Okay? Get our, the object at distance d naught from the surface. We use our light ray parallel to the axis, and it should reflect, right? Reflect away from the mirror because it's a convex surface. Imagine the convex surface here, we have a normal that's going to be somewhat like that, right? So the rays is going to diverge. Very important, convex, concave surface. Very important between convex and concave surface. I'm going to write that down here for you. Concave surfaces, concave mirrors converge light rays. Convex mirrors diverge the light rays. Okay? Diverge the light rays. That's an important difference between them. So that's the first light ray. Parallel to the axis, the light is reflected in this direction. And what else? It passes through the center of through the focal point. But it's the focal point on the right side, right? Because the center of curvature now is on the right side. Don't forget, the surface is like that. Here's our first light ray. Next, right? Our second light ray is going to be the one that goes towards the focal point. Okay, here you go. See, it's going towards the focal point, but once it's incident at the surface of the convex mirror, is going to be reflected parallel to the axis. Okay, and we have to extend we have to extend this light ray here, and the intersection of this light ray with the extended part of this other light ray tell me what's the position of the image. And here you go. Here's the other light ray. Passes through the center of curvature, right? It reflects back on itself. And here, where the image is formed, we see the same thing here in this simulation. Let's see if I can get concave mirror. How do I change that? Concave mirror, convex mirror. There must be a way. Let's see here. Oh, must be the center of curvature. Nope. Oh, what a shame. The focal point. Oh, yeah, the focal point. Yeah, but they didn't come up with the, the surface of the mirror, unfortunately. See, just by adjusting the focal point, yeah, they have the concave mirror, but they don't show the convex mirror for some reason. Okay. This mirror works in a rather simpler way than the other mirror. Why is that? Because the image will always be smaller than the object, always. Okay? No matter where the object is located, the image will always be smaller. And we can see that from the equation as well. See that how it behaves? There must be something wrong with this simulation. It's still saying concave mirror, it's not concave mirror. Let's see, simulation, click here to the next, move the tip of the object. Okay, well, what we have is exactly what's supposed to be, okay? So here you go, see the light ray parallel to the axis is reflected away and its extension passes through the focal point. Light rays that pass through the focal point. This one, the light ray that pass through the focal point is reflected parallel to the axis of the mirror. And here's the extension. And this, let me get this one a little bit closer. Okay, yeah, better now. And now it's the center of curvature, okay? So that's the light ray parallel to the axis, that's the light ray that passes through the center of curvature, and that's the light ray that passes through the focal point. Okay, and we can go ahead and next convex mirror. The behavior of convex mirrors is far simpler than that of a concave mirror. Okay? We start with the equation here. Start with this equation. For convex mirror, the focal point is going to be a negative number. Okay, so I'm going to put that for convex mirror. For convex mirror, f is less than 1, is less than 0, or magnitude. Let's see here. Magnitude of f is equal to minus f. That's how we denote. Okay, so we can go ahead and write like that, you know? Like that. Put the f here inside, but put a negative sign as well, right? Or, right? Or f equal to minus, like that. And now we go ahead and passes the d naught to the other side. So this ratio will always be less than 0. Di is always less than 0. So what does it mean? Image is virtual. Okay? Is always virtual. For, here you go, even better, for positive, right? I'm going to be even positive d naught, comma, image is always virtual. Even better if there will be a case in which d naught can be negative, okay? But we're not going to cover that here in this course. That's why I'm making this distinction. It's always virtual. And we can write that down, write down in GI. There you go. What we're going to do here now, I'm going to do like that. I'm going to write down di. I'm going to put d naught, multiply and divide by d naught. And I'm going to multiply and divide by f, by the magnitude of f. So we can analyze that, right? In the next step, we put them under the same denominator, right? And my DI becomes FD naught like that. We have this negative sign passed to the other side. Okay. So, always going to be negative, right? And now let's look at the magnification. Here's the magnification. DI over D naught. Take it out. That's my DI. The D naught that we have upstairs cancel out this D naught. Right? And what else? This negative sign disappeared because we're taking the magnitude, right? And then what else? Note that this term here is greater than this term, right? Note that whatever is downstairs is greater than whatever is upstairs. So what does it mean? It means that this thing here must always be less than 1. So the magnitude, the magnification will always be less than 1. So whereas the concave mirror, we had like 3 different regions, right? That we have to worry about. The convex mirror has just 1 region that we have to worry about. So it's simpler than the other one. And I want, here you go. Here you go. Convex mirrors converge the light rays. Concave mirrors converge the light rays. Convex mirror divert the light rays. And we are done with this chapter. Here you go. Mirror equation, the magnification equation, formation of image by spherical mirrors, okay? 2 different types of mirrors. And what we have next is going to be length. Any questions? So make sure you practice a little bit of this simulation, okay? And I'm afraid I can't figure out how to change this thing here. Okay, that's the position, the focus. Yeah, the surface appear, but the convex surface doesn't appear for some reason. I do not know why. There might be somewhere here that you should be possible to adjust it, but I can't find it. Or most likely the thing is, the simulation is had a problem. Okay. So 11:21 right now. We are ready for our next break. 11:21 a.m. to 11:36 a.m. Right? And I see you in 15 minutes. Oh, sure. Okay, I'm back here. So we covered every section of this chapter. Let's write it down. This theory is not that difficult, right? It's just geometry. That's what it's all about. And you're going to see that when you start talking about lenses, it's going to be kind of similar as well. It's a little bit more complicated than mirrors, but it's rather similar. Because mirrors are simpler, we cover mirrors before lenses. And let's write it down, sections of chapter 25. Wavefront and rays. Here you go, 25.1, 25.2, 25.3, 25.4, 25.5, 25.6. Okay, now it's just a matter of changing the titles here. Wavefronts and rays. That's one of the postulates of geometrical optics. Okay, light behaves like rays. The reflection of light the formation of image by a plane mirror, the formation of images by a plane mirror. Then we have spherical mirrors. The formation of image by a spherical mirror. By spherical mirrors. The mirror equation and the magnification equation. And the magnification equation. So we covered everything, and now we're going to cover something else. Chapter 26. I need to turn on my video. Here you go. You cannot see me, right? Just saw it now. Just notice it now. Let's see if anybody has a message. So let's look at the postulates of geometrical optics. Okay, let me tell you about the postulates of geometrical optics, which applies both to mirrors and lenses. The first postulate you already saw. Okay, light behaves as though as they travel in a straight line, like a ray. That's one of the postulates of geometrical optics. You saw that, right? Another important postulate, okay, is light takes travels through the path of least time, not least space. Okay, very important. Okay, it is this postulate. That results in the so-called law of reflection. Okay? Angle of incidence is equal to angle of reflection. Angle of incidence is equal to the angle of reflection. Okay? Which other postulate we need here? Okay, and I'm going to introduce another postulate that is used in lenses. Okay? There is this other postulate that is this other postulate that is used for lenses. It states the following. There is an important optical property called the index of refraction. Okay? The index of refraction of a material, refraction of a material, the index of refraction N of a material is given in terms of the speed of the light N equal to C divided by V. Okay? Okay. For the sake of this course, N is always greater than 1, greater or equal, always greater or equal than 1. N is always greater or equal than 1. According to this equation, C is the speed of the light, speed of light in vacuum, and V is the speed of the light in the material. Okay? So those are the three important postulates that you have to keep in mind. The postulates of geometrical optics. Okay. Because, here you go. Because different materials have different, because light, right, travels at different speeds, in different optical materials, these result in some rather interesting phenomena. The phenomena, one of them being the phenomena of refraction. instead of reflection, okay? So keep in mind, we have reflection and refraction, okay? Reflection and refraction. Refraction is whenever light travels from one medium to another of a given index of refraction to another of different index of refraction, okay? You know, there are tables for the index of refraction of different media, right? And it's a good idea that you memorize at least the most important ones, okay? For instance, the vacuum in space. The index of refraction of vacuum is 1, exactly equal to 1. Air. The index of refraction of air is approximately 1, very close to 1. Okay? It's not much different. There is a slightly larger than the index of refraction of 1. But for the sake of this course, you can use it as being 1. Index of refraction of water, you know, N is approximately 1.33. Okay, and then you have, you can go to the internet. Let's see here. Let's see if you have a table here in this book. The book must have a table here. So those 3 media, I want you to memorize. It's not difficult to memorize. Air, vacuum, and water. This thing is not refreshing. Let's see. Okay, good. Here you go, the definition of the index of refraction. Here you go. That's the table I'm looking for. Diamond, look at the index of refraction of diamond is very high. What does it mean? It means that light travels very slowly in diamond. Oh, there's another one, glass. Okay, glass. Most glasses has a refractive index that's very close to 1.5. It's not difficult to memorize that either, right? And then you have other types of materials. Ice, which is solid water, 1.309. Water, see that? Liquid water, 1.333. Benzene has a relatively high refractive index. Air. Remember that I told you that air has a refractive index very close to 1? Look here at those decimal places here, right? Gases in general has a refractive index very close to 1. Here's a mixture of air, is a mixture of nitrogen and oxygen, right? Pure carbon dioxide has this refractive index, pure oxygen has this refractive index, hydrogen, right? And so on. But what I want you to memorize are those 4 here. Can you do that? From the above values, you can calculate the speed of the light in their respective materials. Okay. Okay, and because of the different speeds when light travels from one medium to another one, it may, in general it does, okay? It may bend its trajectory. And that is a very nice way of visualizing that. Let me see if I can find my illustration to show you refraction. Oh, right in here, refraction in lenses. Okay, so here you go. Light travels in straight lines. First postulate of ray optics, right? We have a source here, we have a point A, B, and C here. Okay, if light is gonna travel from S to A, it's gonna be in a straight line. It's not gonna go like that, you know, in a curved fashion or in different zigzag patterns. It's not gonna do that. Unless, of course, we introduce a medium of different refractive index. Same thing applies to B, straight line from S to B. And, you know, provided the medium is optically homogeneous, okay? Optically homogeneous medium. If the medium is not optically homogeneous and homogeneity is defined in terms of the refractive index, okay? Like in this case, we have air here and we have another second medium, a glass, for instance, or water. So light is traveling through a medium that's not homogeneous. One refractive index from here to here, another refractive index from here to here, okay? It is possible to prove, according to the postulate of least time, that light rays that travel from the S to B are going to be, is going to take a turn here at the interface, okay? The turn can be either towards the normal or can be away from the normal. Depends on the relative refractive index. Okay? See here, this dashed line is the path of least space. Okay? Whereas this other, the actual path of the light, is the path of least time. Light spend less time traveling this distance here than if traveling this distance here. It may be least space, but it's not least time. Okay? So that's what we end up finding out. If we apply this principle of least time, then we end up with a very important equation that we call it Snell's law. Remember, it's not a law, but it's a consequence. It's a consequence of the principle of least time. That's going to be given by the following equation. According the angle of refraction is given by the so-called law, Snell's law. Snell's law, which is a consequence of the principle of least time. This time, okay? And here you go, that's the equation. That's the equation. The refractive index of the first medium times the sine of the angle of incidence is equal to the refractive index of the second medium times the sine of the angle of refraction. Can you memorize that? We can prove, right? The above equation can be proven by setting the path of least time, okay? We don't do that here. 2 minutes to go, huh? So recall that for reflection, right? For reflection, we have a different equation. We have a different equation. All right? Now, and don't forget the angle of incidence. The above angles are measured with respect to the normal, to a direction, are measured with respect to a direction, normal to the surface, to the interface, right? Interface of the two media. Now, let's do a very simple example. Find the angle of refraction for an angle of incidence of 0 degrees. That's easy. That's not difficult. Okay? We're almost running out of time. Let's see if I can do that. Here you go. We start with this Snell's law. Solution, right? Solution. That's the Snell's law. I don't even need the refractive index to solve this problem. The angle of incidence is 0 degrees. Consequently, sine of 0 is what? Is 0, right? So the left side of the equation is going to be 0. And if the left side of the equation is 0, the only way that this equation is going to hold is that if the sine of the angle of refraction is also equal to 0. Okay? Like that. Like that. Okay, so simple example. But then we have more complicated types of examples that's going to depend on the sine of the angle of incidence and the refractive index of the two media, okay? So it's 12 noon right now. And we can stop. Do you have any questions? I will save this document, right, in PDF, and I will upload also the recording of the class. If you don't have any questions, we can stop, and I'll see you on Wednesday, okay? See you then. Thank you for being here.